We present our research titled Visuo-Tactile based Predictive Cross Modal Perception for Object Exploration in Robotics. Humans infer physical properties via manipulation using both vision and tactile sensing. Particularly, tactile sensing has been found to be crucial for exploration and dexterous manipulation. Human-like perception and exploration has been a source of inspiration in robotics and is an active research area. A key prominent working theory of such human perception is that of predictive processing, according to which it is hypothesized that humans learn an internal model of the object interaction to engage in its exploration and manipulation. They infer the object properties by predicting the expected percepts or observations and also leverage the cross-modal information from visual modality. Inspired by such principle, in this work we address the problem of cross-modal perception of estimating the mass of an object using non-prehensile pushing action, which is simpler and robust compared to other interaction approaches. We sought to investigate two research questions. Can the shape information be used as a prior to improve mass estimation? And how can we refine the prior prediction over time? However, there are certain challenges associated with the problem, such as how to represent and estimate the shape of the object, how to handle the weakly correlated visual and tactile observations, how to infer the mass of the object by non-prehensile pushing and raw visuo-tactile observation, and how to iteratively and efficiently improve the cross-modal visual prior prediction for lifelong learning. To address these problems and challenges, we propose a novel framework where the shape is estimated by a low-dimensional superquadrix and the information is used by a Gaussian process regression function to predict an initial prior of mass, which is utilized within our dual filtering approach to improve the estimation via non-prehensile push interaction. We then exploit the estimated value to refine or iteratively train the regression function efficiently using a novel surprise formulation. This is our proposed framework with the dual filter block in detail. In the subsequent slides, we present the details of the framework with a working example. The robotic system comprises of a UR5 robot with a tactile sensor and a Panda robot equipped with a vision sensor. The Panda robot, the object is placed in the scene and the Panda robot goes to few fixed locations to get a complete shape information of the object. The initial point cloud from the multiple locations is captured to compute the initial shape parameters. We utilize superquadrics which offer rich shape vocabulary encoded by lower dimensional real 5-dimensional parameters defined by the implicit function. We utilize a robust estimation approach recently proposed by Liu et al. The estimated parameters of the superquadrics is utilized and obtain the initial prior over the mass and also compute the push action affordance. The UR5 robot interacts with the object, obtaining visual and tactile observations, which is utilized within the dual filtering step. The dual filter is based on uncentered filtering approach with key novelty. We use a constraint sampling approach to ensure the constraints of the parameters such as mass cannot be negative are respected at each time. Further, for this work we use analytical model of pushing as process and observation model. To update the belief at each time step, the predicted observations are compared with the actual observations to update the belief of x, y, and theta and the mass. X, y, theta are the pose of the object and mass is the one which we are interested in. The estimated value of the mass at the end of the interaction is utilized to compute a surprise value based on the initial prior prediction by the Gaussian process regression. This is the negative log likelihood function. A higher surprise means the shape mass prior is new to the function and the lower surprise denotes that the initial prediction was close to final estimation. This ensures the sparsity and makes the Gaussian process regression much more efficient. To evaluate our framework, we designed 3D printed objects whose mass can be varied in different ways. In addition, we also selected 9 daily objects to robustly evaluate our framework. Here are a few clips of our robotic system interacting with different objects using our proposed framework. After each interaction, the absorption process is iteratively trained based on the surprise formulation. We can observe the supercortex-based estimation is able to capture the shape of all the objects quite accurately and also verify the proposed cross-modal prior improves the mass estimation resulting in faster convergence. We can also observe how the surprise formulation leads to improved efficiency of the GP training without affecting the prediction capability. Thus, all the critical mass shape information were utilized in training the GPs. In conclusion, we present a novel Visuo-Tactile based predictive cross modal perception framework and a human inspired surprise formulation to iteratively refine the cross modal prior prediction of mass. In future, we would like to investigate more intricate cross-modal functionalities such as surface friction based on color or reflectivity, or have this cross-modality across different robot morphologies taking into account the embodiment. Thank you.